Hey guys, lesson 9. We're going to continue with chapter 5 from the book about the traveling salesman problem. Last time we have done the first 2 points, first 2 objectives. Now we're going to move to the last 2 from this chapter. The third one is to use the minimum spanning tree method to find the lower bound. And the last point or last objective that we need to talk about is to use the nearest neighbor algorithm to find the upper bound. So you will have 2 methods for finding the upper bound. You can choose from unless it's specified which one you need to follow. So let's look at the first objective, and that's the using minimum spanning tree method to find the lower bound. If you read through, you might get confused by several new words or several new vocab, as finding the residual minimum spanning tree and then adding the cost of reconnecting the deleting vertex. So I would just say you can read through, you can pause the video, read through, but I will explain you the point by point directly on the example. So example 1 says you are given the table of least distances for a network. This is shown. And usually you are given the vertex that you need to delete or several vertices that you need to delete. If that's not given, that means you have to delete every single one in turns. But don't worry, that's not very often that would happen. So in this case, they tell me that I should delete the vertex A. So I can just forget whatever the vertex A, like it doesn't even exist. And then I'm going to look for the residual minimum spanning tree. That means it's the one that stays there when I delete the vertex that was given to delete. So I am looking for the lower bound minimum spanning tree from the rest of the table. That means you're just going to follow the algorithm for finding the minimum spanning tree on the table. That means the prime algorithm. So you can choose which vertex to start from. I will choose to start at B. That means the smallest number is 8. That gives me BD. BD is my first arc, and then D will happen to be my second column, and I can delete B and I can delete D as well. I'm looking at B and D. The smallest number is 14. So that means DE is the next arc. And E will become the third column. And I'm deleting this. And then the last one is 18, what gives me EC. So this is residual minimum spanning tree. Okay. If you want to sketch it, the weight of this is 32, so 40. And then when you want to sketch it, you have B, you have D, E, and C. B to D, D to E, E to C. Okay. Now, the lower bound is though, I'll write it here. You find the lower bound. If you read the algorithm properly, then it is when you add the weight of the residual minimum spanning tree residual minimum spanning tree plus the weights of 2 shortest arcs. To the deleted vertex. So in this case, I had 40. And then you can go back and check what arcs were the shortest one from the A. So A, the shortest one was B, that was 11, and C, 13. So B and C, so 11 plus 13. So when you look at it, I connect A is here and then to C. So AB was 11 and this one was 13. So together I have the lower bound 64. And remember, we checked only vertex A, but if the vertex that you should delete is not given, then you need to do the same process for every single vertex. The reason why is because you want to make the lower bound as high as possible. So the interval of the optimal solution will become narrower and narrower. Okay, but because they told me to delete only vertex A, I'm going to follow, and it's actually enough to do it only with vertex A for the reason that we will discover in case B. You can recall in your mind what the Hamiltonian cycle means, and Hamiltonian cycle is the tour that every vertex is visited only once, exactly once, and then you come back to the original vertex that you started with. And when you look at the picture of the one that we draw now, the residual minimum spanning tree together reconnected with the A, this is a Hamiltonian cycle. And as soon as this represents the Hamiltonian cycle, then this lower bound is the optimal solution. Okay, so that's reason number one. Let's do the big case here. So to the question whether this lower bound represents an optimal solution, you can say yes, it does, or it is an optimal solution. Because it represents the Hamiltonian cycle. So that's one way how you can look at it. Another way how you can look at it is by comparing this value with the upper bound. We found this is exactly the same problem as we discussed in a previous lesson. It was example 6, we were looking for the upper bound, okay? And you may recall, you can go back, or I just took the screenshot, you can see the upper bound was also 64. And when the lower bound and upper bound are the same, then the solution is optimal because it guarantees that it's the Hamiltonian cycle. So the second question is asking you to do the same thing by deleting the vertices A and then G. We will find the two lower bounds and then we will need to decide which one is better. Okay, so I will do the A and then I will do the G, like I'll speed up the video, so because it takes a long time, okay? Or you can just pause it and then skip it to the solution once you are done, so you can check, okay? So now I'm going to do the prime algorithm, except I need to first delete A, and I'll delete the A from here, so I'm only following the B. I'll start at B. So when you look at that, then the lowest one is 121. So residual minimum spanning tree would be BC. It's 121, and C will become my second column, and B and C are cancelled. Now the shortest one here, or the smallest value, is 155. What gives me BE? 155. E is the third column then. Now the smallest one is 131. That is EH. 131 is cancelled. Then I have H is number 4. So the smallest one is definitely 70, HF. And then F will become number 5. F cancelled. Then I have the smallest one is 144. That is FG. FG 144. G will become number 6. And then the last one is GD. GD 155. So when you look at the weight of this one, weight would be, let me add it up, this is something, so 7.776 miles. Now if you sketch it, so I have BC and BE, so E, B, C, and then I have EH, HF, FG, and GD. Now I'm going to reconnect the A, the smallest, the lowest numbers are 47 and 84, so B and C. So this A here. So then the lower bound when vertex A was deleted would be the weight of residual minimum spanning tree, what is 776, plus the cost of reconnecting. So AC was 84 and BA was 47. So together the lower bound is 970 miles if I deleted the vertex A. I'm going to do the same with the G. So I am deleting G first. G and G deleted. I'll just want to see the smallest one would be 155 and 144. Okay, so I'll delete these. Okay, I'll start with A, let's say. Actually, doesn't matter which one you start at. So AB is 47. This is residual minimum spanning tree.
Then B, so I, by. Now the smallest one would be 84. 84, so C is the third one. Now the smallest one would be AE. 120. This is 4. Then the smallest one would be 131. So that is EH. 131. That is number 5. Then I have, let me see, F is the smallest one, HF, 70. F, bye-bye, number 6. And then the last one is FD. FD, that's 220, that's 7. So then I have the weight. Weight here of the residual minimum spanning tree would be 1112, so to 672. Okay, and then I have, I can draw it. So I would have A, and B, and C, and E, because E continues to H, so I put it on the right side. This is H, this is F, and this is B, and this is either B or C, B or C.
So the lower bound, if I deleted the G vertex, would be 672 plus, and now I need to reconnect the G. So the smallest one where G goes with F and G goes with D. F and D. So like this would be the G. So 144 plus 144, and how much was that? 155. So the lower bound here would be 971 miles. Now we found it. We're going to look at the B case, because we had lower bound for deleted vertex A was 900, how much was it? 907, and lower bound for deleted G was 971. And we said the better or the higher the lower bound, the better for us, because it narrows the interval of the optimal solution. So the lower bound is 971 because it's higher value, because it is higher value. So this narrows interval of optimal solutions. The interval optimal solutions. Okay. And C case, so this would be C case, taking your answer to B using the better upper bound, 1237. That was again from before. Write down the smallest interval that must contain the length of the optimal route. So you can say that the 971 was the lower one. Then there will be the optimal solution. Optimal solution. And then it's less or equals to 1237 that was given here, okay, from before. You may ask, why did I use here the inequality sign without equal, and why did I use here also equal sign? Well, because I know that 971 that I've seen in here on the picture, here, I know this is not a Hamiltonian cycle, because I will need to visit at least one vertex twice, because A doesn't connect to D, for example. Okay, and because I know it's not a Hamiltonian cycle, I know it's not the optimal solution. That's why I have chosen in here only the inequality sign without equal. However, for the upper bound, we are not sure. So that's why I put it might be an optimal solution, but I do not know that. So that's why I put the equal sign there. So now let's look at the guided practice. So we have the network that shows the least distances. And in this time, we need to do the same thing, but I don't have the table. So what I can do is just to ignore, because I'm deleting the vertex A, that means I am also deleting this one is not there, this one is not there, this arc and this edge is not there. Okay, so I'm only looking at, maybe it's better if you rewrite it, so B, D, E and C. So BC is 7, then BD is 13, and BE is how much? 10, and EC is 16, and then I have DC is 9 and EED is 12. But if you see directly from your picture, obviously no one needs to redraw it. So I delete it and I'm looking for the lower bound of the traveling salesman problem for the network. So what I need to do is to find out the residual minimum spanning tree, right? So because I am given the picture, I'm giving the network, I'll choose to follow the Kruskal one. So Kruskal algorithm, so I know the BC is the shortest one. And then I have CD is 9. Do not forget to check for cycles. And then the last one, let me see, is BE is 10. And I'm finished now because all vertices were included. So the weight here would be 26. Weight of the residual minimum spanning tree is 26. And that's why the lower bound, when I deleted the A vertex, would be 26 plus, and I'm going to check the deleted one. If I want to reconnect the deleted vertex, if I want to reconnect to the network, the shortest one would be 8 and 11. 8 and 11. So plus 8 and plus 11. What gives me 45. If you want to sketch it, of course you can. BC, CD, BE, and the shortest arcs with the A were BD, so, sorry, not BD, AD, A, and then AE. So this would be 8 and this would be 11. Okay. Now, for the B case, you need to state with reasons, so do not forget to mention the reasons, whether the answer represents the optimal solution. Yes, it is optimal, because when you look at the picture, you can see it's a Hamiltonian cycle. As it is a Hamiltonian cycle, it does represent, or it must represent, it represents the optimal solution. So let's look at the next one. I have a council employee that needs to service 5 sets of traffic lights. They are located at a position A, B, C, D. I have the table of the distances, least distances in miles. This is important when you want to interpret the solution. And you know that she will start and finish at A. Start and finish at A, wishes to minimize the traveling distance. So you can pause the video now, check, delete the A, then delete the B, and again we will check together what is better. Okay, I will speed up the solution then. If you want to reconnect A, the smallest ones are 11, 13, B and C. AC 11, AB 13. So together plus 13 plus 11, what gives you 50? DBDC. So the second part of the lesson is looking at using the nearest neighbor algorithm for finding the upper bound, because the first method that was introduced last lesson can be hard to follow for the large networks, as selecting the shortcuts is difficult and might be time consuming. So let's look at the new algorithm that is offered here. And then unless it's stated in the question that which algorithm you need to follow, then you can choose. In this case, you're going to also select each vertex in turn as a starting point, and you go to the nearest vertex which has not yet been visited or selected. And you're going to repeat this until all vertices have been visited and you have came back to the starting vertex using the shortest route. If you do this, once all the vertices have been used as the starting vertex, then you can choose the tour with the smallest length as the upper bound. Because remember, the upper bound is better when the value is lower, because it narrows the interval of the optimal solution from the upper limit, from the upper value. So let's look at it, how it works on the example. So example 5 says we need to apply the nearest neighbor algorithm using A, B, and C. So you don't have to go for every single one. They just told you to follow it for A, B, and C. So I'm going to write it here. So if I'm starting with A, so A, the shortest one or the nearest one from A is definitely C. So when I pass 7 units, then I'm at C. Once I'm at C, the shortest one or the nearest one is E after 6 units. Then I'm looking at E, that is the next one that has not been selected yet is 14, because 13 has been selected already and also 6 was selected already. So then I arrive to B vertex. Then once I'm in B, I'm looking only at the column B. So the shortest one is 24, and that will get me to D. And now from D, I have to go back to the starting point because I've visited every single one, and that is 29. And then I get back home to A. And the distance that I passed was 29, 24, 14, that's 80. Next one, if I'm starting at B, I'm going to delete this. Please do not confuse it with the prime algorithm on the matrix, when you apply it on the matrix, because in case if it's prime, then you're always looking for the lowest value in every single column that has been already marked. While in this algorithm, you're only looking at the one column, the recently visited vertex. Okay, so I am starting at B, the shortest one or the nearest vertex with the vertex with the shortest distance is A after 8 units. From A, I can go to C because that's the shortest one. Once I'm at C, the nearest neighbor is E, that is 6 units, and then I'm at E. From E, I can go to D, 21 units. And then from D, again, I have to go back to my original vertex, and that's the B. Now, when I add these ones up, that's for 66. And then last one is C. If I'm starting at C, you can pause the video, try to complete it on your own. So C would be 6, that's I will be at E. E is 13, is the smallest value that gets me to A. 8, that will gets me to B. Then 24, I'll get to D. And then from D to C, that's 23 units. And add it up, 47, 45, 74. And then I have upper bound for if I started at A is 80. Upper bound if I started at B is 66. And upper bound if I started at C is 74. And obviously the upper bound that is the lowest is the best. So in this case, the upper bound is 66 because the smaller is the better. So as a reminder that I have already mentioned is please do not confuse the nearest neighbor algorithm with the primes algorithm. In the nearest neighbor algorithm, you're only looking at one column. In the primes algorithm, you're always looking at all columns that have been already selected or marked. So let's look at the guided practice. If you want, pause the video, you do it on your own, and then you can compare, or if you get stuck, you can play the video to find where your mistake is, or even if you cannot understand with a video, then you can ask me online or in person, obviously. So we have in example 6, we have company that is printing 6 magazines, RSTUVW, each week. The printing equipment needs to be set up differently for each magazines, and the table shows the time in minutes needed to set up the equipment from one magazine to the another one in minutes, so that's quite a long time. In the A case, they just want you to find out how long would it take in total to set up the equipment if they were printed in this order. So I just need to read the values from the table. So if I want to go from R to S, that would be 150 minutes. And then from S to T, that's 210 minutes. Then the next one is U, and from T to U is 120 minutes. Then from U to V, U to V it takes 180, VW takes 300, and W to R it's 240. So when you add this up, it's 1200 minutes. Now let's look at the B case. Show that there are two nearest neighbor routes starting from U. So I'll do it here. If you look at the B, I'm starting at U. And as soon as you go from U, there are definitely two because you have 120 are the same values. So you can either go, this is 120, will take you either to S or it will take you to T. Okay, and then this would be enough to show that there are two nearest neighbors because they didn't ask us to state it. Show that there are, yeah, that should be fine. But if the question asks you to state the routes as well, then we need to finish it. So in this case, I'm going to finish it as a matter of the practice. So 150. Then I have goes to R, it's 120. Then I'll go to V, and from V I go 150 to T. Then I go, let me see, this is 180, goes to W. Then it's 270, goes to U. What is 990? And then when I go from T, the next one is 150, is the shortest. Then from V to R, that's 120. From R to S, it's 150. From S to W, it's 240. And from W to U, it's 270. In the C case, similar story, except you need to show there are three nearest neighbor routes starting from V. So if I start from V, let me see, the shortest one from V will take me to R, 120. But once I am in R, there are two possibilities in R because I have 150 that takes me to S, or 150 that will take me to U. So 150 or 150. And then if I follow this S, from S, if I continue, then 120 will take me to U. Another 120 will take me to T. And then 180 will take me to W. And from W I'll get back to V, that would be 990. Now if I'm at U, then the situation will repeat because 120 will either take me to S or will take me to T. If it take me to S, then and I continue, from S I can get to T. From T I can get to W, and from W I'll get after 300 units to V, and then the second one from T I'll get to from T I'll get to W, W because this is fine, and then from W I'll get to S, and then from S I'll take 210 and gets me to V. So that would be 1080, and this one would be 1020. And then finally decase, selecting the value that should be given as the upper bound. Remember, it must be the lowest value possible. So in this case, the upper bound would be 990 because it's the lowest value. Give a reason for your answer. So because it's the lowest value. And you can also mention because it guarantees that it narrows the interval of the optimal solutions the best. So in the last example, the table shows the least driving distances between cities A, B, C, D, whatever, up to G. And the distances are given in miles. The least distance between A and D is the X. We don't know that one, but I know one information about X, and that is that X is less than 126. Bent is planning a tour that they want to create an itinerary that will visit each town at least once, but minimize the total distance traveled. And they identified the nearest neighbor routes from B and A, and finds that the sum of the lengths of these routes is 1419. And the question is to find the X and then decide what's the upper bound for the optimal length of the Ben's tour. So let's look at it step by step. Because I know that they already found out the nearest neighbor routes, these ones, from B and A, and when I added up, they got 1419. That's where I need to start, right? So I'll do it here. If I start from B, then from B, nearest neighbor is E. From E, the nearest neighbor is G. From G, I'll get back to, no, I'll go back, I'll go to D. Once I am in D, then I have 56 is the shortest one, but I already been into E, so I have to go to A, that is X. So from A, it's the nearest one is F, that is 157. And then it's from F, I can go to, let me see, C, that's 211. And then finally, I have to go back to B, and that will take me 92 miles to get back. So this one would be, let me calculate, 648 plus X. The second one, if I start at A, then the smallest one is definitely X, because the smallest value that is given here is 129, but I know X is less than 126, so X must be the smallest one. And that will take me to D. And then from D, I can go to E. And then from E, I'll go to G, 43. And then from G to C. And then from C, that takes me to B, 92. And that will take me to F. 157 will take me back to A. So in this case, I'll get 639, also plus X. And because they told me that their sum is 1419, I'll just use this information, plus X plus 639 plus X is 1419. And this gives me 2X, on the other side will be 132, so X will be 66. So in the B case, I need to find the upper bound for the optimal length of the bends root. So in this case, I would have, if I had the upper bound starting at B, then it would be 648 plus 66, what gives me 714. And if I have the upper bound starting at A, then I have 639 plus 66, what is 705. So obviously your conclusion would be EUP upper bound is better, that is, the value is better when it's lower, so 705 miles. And finally, the last slide, your turn. Please try these self-practice questions from set 5C and 5D. As always, the answers are at the end of the book and the detailed solutions can be accessed on this website. In case you get confused or you are not sure where your mistake is and you need to clarify something further, you can find me anytime you do the questions right away, either online or during the school days. Obviously, you can come for the face-to-face consultation or discussion. Otherwise, I'll see you in the tutorial on Monday afternoon. I'll see you later. Bye-bye.